In this session, we are briefly going to understand the process in which you'll create a k-means clustering model from scratch. We're essentially going to look at the different steps that are involved in the model building process and then look at implementing all of it in Python. The very first step here is to choose a number of clusters, that is a value for k. I'm going to choose a value for k as 3 for the given data and for the given problem that we are trying to solve. So the number of clusters can be chosen based on various methods like elbow method or calculating the sellout coefficient for varying values of k and thereby look at finding the appropriate value of k. But in this particular exercise, we are going to resort to arbitrarily selecting the value of k. In one of our upcoming sessions, we'll deal with all of these different methods that I'm talking about now. Step number 2 is centroid initialization. We now need to choose the initial centroids in the given dataset. For the given data points, as you can observe here within this particular plot, we are randomly choosing the centroids to be these three different data points, C1, C2, and C3, as I have highlighted here. So C1 and C2 can be quite adjacent to each other since we are randomly choosing. We are now randomly choosing initial centroid values. Initial centroid values. Okay, or initial centroids to be more precise. So later we look at recomputing the centroids in our subsequent step. Let's now consider that these different data points C1, C2 and C3 are now the initial centroids. In step number 3, we are going to assign a cluster label to every single data point here. Let's consider that this is a data point that we are currently investigating, which I'm denoting it as X. Now I need to assign a cluster label to this. So what could be the cluster label now? So I am going to compute the distance of this particular data point with respect to all other cluster centroids that you're observing. So that is X and C1, X and C3 and X and C2. I'm calling the distances as D1, D2 and D3 respectively. We clearly can perceive that distance D3 is minimal of all. That is, the cluster centroid C3 is closest to data point X when compared to the other two cluster centroids. And hence I am going to assign a cluster label of 3 to this particular data point. So likewise, we conduct this exercise for all the given data points. If you are considering this data point, we clearly can know that distance D3 is minimal when compared to D1 and D2 here. So the cluster label for this particular data point is going to be 3 again. Step number 4 is going to be recomputing the cluster centroids based on the newly formed clusters from step number 3. In step number 3, all what we have done is to assign cluster labels to every single data point here. Since we have these newly formed clusters, that is cluster 1, cluster 2 and cluster 3, we're now going to recompute the cluster centroids and we are no longer using the randomly selected initial centroids, which is a poor practice to select the centroids, right? So within cluster 1, I'm considering all of these data points and compute the mean. So mean of all the xi's that are present within my cluster 1. This is going to be my centroid C1. So similarly, mean of all xi's that are present within cluster 2 is going to be my centroid C2. And then mean of all xi's that are present within cluster 3 is going to be my C3 here. Okay. Since I have recomputed my cluster centroids, I can repeat step 3 here. That is, reassign the cluster labels to all of the data points. If I reassign the cluster labels to all of the data points, then the clusters will change. And then you recompute your cluster centroids again. So I can repeat step 3 and 4 till I attain convergence. So what exactly is convergence here? The convergence could be that the centroids do not change much, or the points that are defined for different clusters do not change much, or the maximum iterations that we have set as a limit is reached. Either one of these can be considered as convergence criteria. So we're now going to implement all of these steps that we have learned and this particular convergence criterion where we are checking for centroids if they are not changing iteration after iteration, and then we stop the iterative process then and there. Okay, so let me switch back to VS Code and try and load the dataset first. I have listed down all the steps that we have discussed so far here itself, right? So I'm going to make use of load underscore dataset function from Cbon. In order to load iris flower dataset, I'm assigning this to a data frame called data. I'm essentially going to consider only two different variables because I also would want to visualize the data here. So two-dimensional visualization is more practical for perceiving or for humans to perceive properly, right? So sepal length and petal length are two different variables that I'm now considering to be my x variables here. I'm assigning this to a particular data frame called x. I also would want to normalize this data since I'm computing the distance. Any distance-based algorithm or model that we are essentially creating needs to have this data normalization or standardization step as one of the pre-processing steps. So I'm going to import the min-max normalizer or sklearn datasets, right? From sklearn.preprocessing. From pre-processing module, I am going to import min-max scaler. So I'm going to instantiate this particular class and call the object as scaler. Use this particular object called scaler and apply fit transform onto the given x data. If we are having test set defined separately, then you are going to make use of the same object and not do fit transform, but just do transform for the reasons that you are completely aware of. Okay. So now I'm going to reassign this to x. Since this is not a data frame, once you do a min-max normalization, I am essentially looking at converting this to a data frame by enclosing this particular object into pt.dataframe. I also would like to provide the columns here. The columns are nothing but the same, just the same columns that we have provided in the previous step. We finally look at the shape of this particular input data that we are going to consider for executing the different steps that we have discussed so far. So step number 1 and step number 2 involves choosing the value of k, right? Choosing the value for k and also initialize the centroids. This is a random initialization that we have spoken about. Okay, cool. So the value for k here is going to be 3 as I have discussed earlier. So the random initialization of centroids can be done by simply making use of np.random.choice function. So I'm going to randomly select 3 data points of all the data points that there are, which is nothing but x.index. So of all the indices that are present within my input data, I am going to randomly select 3 of them. Why 3 different centroids? The number of centroids should be same as that of the number of clusters, as we clearly know this. So I'm calling this as centroid underscore indices, right? So making use of this centroid indices that we have defined in this particular step, I'm going to create this new data frame called centroids. So x.iloc and provide these indices that we have defined in the previous step here within the subscript. So as to determine what could be our centroids data frame, let's also inspect what the indices are. So we can perceive that all the indices that are available within the centroids data frame match with whatever indices that we have randomly chosen from the given set of data points that we had. Let's look at incorporating step number 3. So step number 3 here is going to be assigning the cluster label. Assigning the cluster label to all data points. Okay. So when I mention to all data points, so I am going to essentially compute the distance of every single data point with respect to all the cluster centroids C1, C2 and C3 here, right? So in order to compute distances, I would want to define a new function called Euclidean distance, which accepts 2 different parameters, centroid and x here. So we simply can consider the first coordinate of my centroid, the difference between the first coordinate of my centroid, the first coordinate of the x data point here, take a square of it. And then you again consider the second coordinate of centroid and the second coordinate of x, take the difference of them and square it, right? So, and then take a square root of it ultimately, so as to compute what we call as Euclidean distance, return this distance altogether. All what I have tried to implement here is to look at finding this particular formula, which is nothing but c11 minus x11 whole square plus c12 minus x12 whole square, right? Where c11 and c12 are the coordinates of my centroid and x11 and x12 are the coordinates of my x data point here. So this is a Euclidean distance formula and that's what I have implemented here. That's all, nothing apart from that. So, but the subscript notation has to be changed. So it has to be 1 and not 0 because we should reference the second coordinate and not the first one in both the terms. Okay. So once we have executed the Euclidean distance function that we have written just now, let us look at iterating over all of the data points that are present within my input data, for which I am going to make use of iter rows function. Okay, so this produces both index as well as the row. So for row index comma row in x dot iter rows, I'm now going to consider this x data point and convert it to a tuple, a pair of coordinates. So since there are only two different variables, sepal length and petal length, we have pair of coordinates that are defined for my x data point. And for every observation or for every data point, I am now going to compute the distance for that data point with respect to all other cluster centroids. So I need to write an iterative for loop which iterates over the different centroids that we have defined in the previous step, right? So which is given by centroids data frame dot iter rows again. So we now have this particular data point pertinent to the centroid here, converting it to a tuple again. So now we have C and X with which you can calculate the Euclidean distance that we were looking forward for. So C and X are now the arguments for this function called Euclidean distance. I am going to write this as a specific column within my input data. So row index is what I need to provide first within the subscript, followed by the column name. What could be the column name? The column name could be an interpolated f string which denotes the cluster distance, right? Which denotes the cluster distance by using this particular cluster val which I'm trying to initialize this to 1 and then also increment this right after this particular statement. Okay, so all I'm trying to do here is to create 3 different columns for every data point which denotes cluster distance 1, distance 2 and distance 3, which actually denotes the distance of that particular data point with respect to cluster centroid C1, C2 and C3 respectively. Okay, so now once we have done this, we actually look at deriving all of these cluster distance columns, right? What are the different columns that we have created newly here? So x dot filter regex string, that is a substring that we are looking for here, is cluster underscore distance dot columns dot toList is going to provide us a list of the different distances or the list of columns of different distances that we have computed so far. I'll make use of this and then provide this within the subscript so that I'm referencing only cluster distance 1, 2 and 3. I'm trying to find which of these is minimal because that's the next step, right? We need to find which of the distances D1, D2 and D3 is minimal of all. So we assign that particular cluster label to the data point. That's the whole point here. Okay. So I'm now going to write an apply function, a simple apply function, which will have a lambda expression here, which indicates row and row dot index. So I'm just trying to retrieve the index of it, retrieve the index of row, where I am trying to find which of the distances is minimal of all, which of the distances is minimal of all, right? So the whole apply function needs to be done at axis is equal to 1. Now we clearly have the cluster label. So row dot index is going to help us understand what is the label associated with the minimum distance that we have computed of all 3 distances, right? So I am going to assign this to a new column called cluster or cluster label, whatever we call it. Okay. So once we have assigned all the cluster labels to all the given data points, we're now going to display what this could be, right? Let's display this first. So the X here is not defined. So this clearly has to be updated to X, not row. There's one more error here, which is an index error. Let's look at what specific point we are observing this particular error. So this is somewhere in this particular statement where we are trying to compute the Euclidean distance in between C and X. And then we are assigning this back to a particular column that we have defined, right? And this has to be updated from ilock to lock. That's the problem. That's the problem here. And now we observe the resultant data. We now are observing that pair of data points, like for the index 0th data, we now observe what is the distance of this particular data point X with respect to C1, which is given as 0.78. And then cluster distance 2 is given as 0.68 and 0.08. Since this is minimal of all 3, we have this cluster distance 3 as cluster label. But this has to be an integer, it should not be string here. So in order to convert that to a string, in order to convert that to an integer, we are going to make use of map function. Let's consider this particular column called cluster label first. Okay, so we are going to map. Okay, we are going to map cluster underscore distance 1 to integer 1. Similarly, cluster underscore distance 2 string to integer 2, and subsequently cluster underscore distance 3 to integer 3. I'll reassign this again back to cluster label column. Finally display X here. So when I display X, we clearly understand that cluster label is no longer a string data type column, but it's an integer data type column. Okay, this is what we have expected so far. Now, since we have found the cluster labels for all of the data points, now is the time that we are supposed to update our centroids. So how do I update our centroids? I simply do a group by this newly calculated column called cluster label, and then finally look at finding the average of sepal length and petal length of all the data points that are defined within each of these cluster labels, right? So let me copy this column sepal length and petal length from above and paste it here and take mean of it, which is going to be my centroids updated, new centroids, as you can say, right? So since you have the new centroids and the old centroids as well, you simply can find what the change is. What could be the change? The change could simply be the difference between a particular coordinate of my updated centroids with respect to the existing old centroid, a particular coordinate of old centroid, right? Or I can simply replace this 0th index with I and write a simple list comprehension that I am now finding the differences, right? I'm now finding the differences of the corresponding coordinates in between the updated centroid and the old centroid for all the clusters that we have. How many clusters do we have? We have 3 different clusters, and hence I'm defining a range object which varies from 0 to 2, right? So we clearly have this list comprehension now, and I can take the sum of all of these differences, and if there is no change at all, then change is here is going to be 0. If at any given iteration, if there is no change at all, or if the change is 0, then I am going to break or come out of the iterative for loop, but I have not defined the iterative for loop yet. So for iter in range of 1000, maybe 1000 is the maximum number of iterations that I'm planning to conduct, right? If I'm observing a particular change at any given iteration to be 0, that is a change of the updated centroids with respect to previous centroids is 0, then I'm going to break from the loop. I'm also going to inspect what could be the corresponding iteration here. Okay, and remember, we always need to update our old centroids with the new centroids. That's it. So this is a whole logic that we need to write. So let me run this particular code, and we clearly can understand we reached convergence for iteration 3 itself. When I restart the kernel and go about running all the cells, you might completely find a different iteration altogether, because the centroids that are initialized might be completely different, because it's a random initialization that we are doing. You see that we have reached convergence at iteration 10. So we simply can try to generate a scatter plot so as to understand how good of a clusters that we have created so far, right? So now let's generate a scatter plot. Let's look at creating figure and axis objects using plt.subplots function, right? So ax.scatter is going to be the method that I'm going to choose now. ax.scatter, and on x-axis I'm going to have the sepal length, right? Sepal length is one of the attributes that I have considered. On y-axis I'll have petal length again, because that's another attribute that I have considered for this model building exercise. I'm going to provide a size of 10 and color of blue, whatever it is. So let me not provide any color at all for now. I've provided a size of 10. I'm also going to set x label to sepal length, because that's what we have considered for x-axis, and provide a font size of 14. And similarly, I'll also set y label. Y label here is going to be petal length. Provide a font size of 14 as well. and plt.show. This is going to generate a simple scatter plot for us, but we clearly do not know what are the clusters that are formed here. So let me create a new list called colors, where I am providing a possible list of colors like blue, green, and black. Okay. Now I am going to make some changes to this particular code. Like I am now going to retrieve the data by cluster label, right? For cluster in range of k, that is the number of clusters, and I can extract the subset data, right? So subset data could be x.ilog, or probably I can reference this particular cluster label here, okay, to be equivalent to cluster plus 1, because it starts from 0, right? I do not want it to start from 0. Or probably you can change this range object to 1 comma k plus 1 and avoid having plus 1 here. Okay, now you have the cluster data or subset data here, to be more precise. So using this subset data, you can do a scatter plot. So instead of x, now I am having subset data. Or let's not worry about having k plus 1 here, but rather have just k and add 1 to cluster here. So with this, we'll be able to generate the scatter plot for every single cluster data points that we are having, but we need to denote them separately by providing color, right? Different color here. So colors, and then I can reference this with a particular index being cluster here, which is defined by the range object that we have had in the first step here. Also provide the size here to be 10. And that's it. So we now have clearly generated a scatter plot. Okay, there's some problem here because we are defining the size twice, which is not necessary, right? Let me run this particular code again. So now we have clearly understood. We have 3 different clusters which are denoted by these colors green, blue, and black. You can also very well go about identifying what could be the final cluster centroids here. The final cluster centroids could again be mapped or identified by using ax.scatter method. But instead of subset data, we are now going to consider centroids. And within centroids, now you are going to have these coordinates as sepal length, and y coordinate should be, or y data should be petal length here. So size is going to be 10 again. Color I'm going to provide it as red so as to distinguish from the existing colors. So this here is going to be my cluster centroid C1, cluster centroid C2, and cluster centroid C3. All of these data points are now belonging to this particular cluster. All these data points are now belonging to cluster C2 or cluster 2. All these data points belong to cluster 1 here. So this is how you can implement all of the steps that we have discussed in the model building process by considering an arbitrary value for number of clusters here. In the whole process, we have read each and every input data point, and for every input data point, we are now computing the distances with respect to all other centroids, and then finally create 3 different columns denoting the distances with respect to each of these centroids. Find which of the centroids or which of the distances is minimal of all. Assign that particular cluster label to a new column called cluster underscore label. Group by that cluster label and update your centroid by computing the mean of sepal length and petal length grouped by that particular cluster label. The updated centroids are now assigned back to the actual centroids, and we are also capturing the change. If the updated centroid is not changing much when compared to the previous centroids, we are going to break from the iterative for loop and then conclude that we have reached the convergence, stating that whatever clusters that you are observing at that particular iteration are the final clusters, where your distance or where your within sum of squared distances is minimal with respect to the cluster centroids. Okay, so that's pretty much all I wanted to discuss with you in this session. Thanks for watching.